Check it out now, y'all.
NanoHub U, online instruction.
Hi, welcome back. We're going to start a few lectures this week that will basically close our discussion of statistical physics. And one of the questions that we've been dancing around for the last couple weeks is this distinction between classical statistics and quantum statistics, and we're going to try to finally sort that issue out. And in particular, this lecture is focused on something that's referred to as the thermal de Broglie wavelength, and the discussion is intended to allow you to make a decision for a given system on whether you're going to need to use classical statistics to describe that system or quantum statistics to describe that system. So we're trying to develop a general criteria that helps you or guides you in that choice. And the criterion we're going to use is based on the thermal de Broglie wavelength of a particle. So there are, of course, important differences between classical and quantum statistics. We've touched on these differences more than once in the past few weeks. You'll recall that in classical mechanics, identical particles, identical objects or particles can be distinguished one from another. So you can actually label the particles, or you can paint them so that you can follow them. Their position as a function of time can be known with high precision. In quantum mechanics, that's not possible because when you get to the quantum level, all electrons, for instance, are identical to an electron, and it's not possible to color these electrons and follow their trajectories. There's uncertainty principles that are related to uncertainty in position, and this basically means that you cannot track the particle over time. All you can do is you can calculate probabilities that the particle will be at a certain point at a certain time. And this characteristic of a quantum system is often referred to as indistinguishability, and it's to be contrasted to the distinguishable nature of classical particles. If we want to, I guess the point is that for identical particles, the wave nature of quantum particles prevents us from determining which of many possibilities have occurred. And so just to illustrate that, I have two particles, particle 1 and particle 2. They're at these positions at some time t, at some time later in time. We also observe these particles. They're emerging from this region of space. And the point is that if the particles are described by quantum mechanics, we don't really know what happens inside that region that's blocked off in blue. If the particles are described by classical mechanics, we can then investigate in some detail what happens inside that blue box. So if we take the blue box away, right, we can see that there are many different possibilities for interactions that could occur. These are just schematic representations, and so we have two particles to begin with. We have two particles that emerge, and in principle, quantum mechanically, we don't know which of these different situations has actually taken place. I think the key point of the lecture that we're discussing right now is that if the de Broglie wavelength of the particles becomes comparable to their separation, then you have to basically rely on quantum mechanics to discuss the time evolution of the system. If, on the other hand, the particles are well localized, the de Broglie wavelength is small compared to the separation between particles, then classical mechanics is appropriate. So we can make that simple insight a little bit more quantitative by just considering a situation of particles. So to begin with, let's say we have n particles in a box at some temperature T. These particles are moving around, and on an average situation, there's basically a radius that describes the nearest neighbor separation between particles. So if you take this parameter S and you multiply it by 2s is then roughly the interparticle separation for the particles in this box. And the question is, what typically is the size of S for, let's say, an atom, for a collection of gas atoms? So you can do that by just realizing that the number of particles per unit volume is going to be determined by this parameter S. So on average, you're going to have one particle in a volume which is 4/3 pi s cubed. So these things that look like circles are really spheres, and the particle is constrained in the middle of that sphere. And since the separation between the particles is designated by this parameter S, right? We can assign an effective volume to each particle, which is just the volume of the sphere. And so that means that on average, the number density, the number of particles per cubic meter, is on the order of 3/4 pi s cubed, where S is this interparticle separation. Now, the key point is that we can estimate what this particle density is, because we know that, for instance, in a gas of classical gas atoms, we have 1 mole of particles, N sub A, in 22.4 liters of gas. And that just means that we have something like 2.7 times 10 to the 25th molecules per cubic meter. And that number then has to be equal to S/4 pi, has to be equal to 3/4 pi s cubed. So from this relationship, we can get an estimate for S. And it turns out S is on the order of 2 nanometers for gas atoms at standard temperature and pressure. So typically in a gas that surrounds you whenever you're in a room on Earth, the gas atoms are separated one from another by about twice this distance. So the interparticle separation is on the order of 4 nanometers, give or take a factor of 2. So that's the classical description of, let's say, the interparticle separation between atoms that are contained in a gas. If we think about that problem, and from a quantum mechanical point of view, you can't think of the particle as a point mass anymore. You have to replace the particle by a wave function, and that wave function is going to have a de Broglie wavelength. And then it becomes interesting to ask, what is the de Broglie wavelength that characterizes these particles when they're in thermal equilibrium at some temperature T? So that's a calculation that's pretty easy to do, because we know what the definition of the de Broglie wavelength is. We also know what the energy of these gas atoms are. It's p²/2m. And this gives us an expression for the energy in terms of the de Broglie wavelength, which I've worked out here. And then from our discussion of statistical mechanics, the Maxwell-Boltzmann distribution law, we know from the equipartition theorem that follows from that Maxwell-Boltzmann distribution function, we know that the average energy of a particle is going to be about 3/2 kT, because the particle can move in 3 dimensions, and each dimension we associate 1/2 kT of thermal energy. So that allows us a relationship between the de Broglie wavelength and the temperature T of the gas atoms, and it's telling us that we can define a thermal de Broglie wavelength, which is just equal to Planck's constant h divided by 3 times the mass of the gas atom times Boltzmann constant times temperature T. All of that has a square root associated with it. And so if we want to decide whether a collection of particles has to be treated as in terms of quantum mechanics or in terms of classical mechanics, what we have to do is we have to compare this de Broglie wavelength lambda to this interparticle separation distance s. And if lambda is much, much greater than s, that means that these de Broglie waves are very large compared to the interparticle separation. Then that's telling us that we probably have to use quantum mechanics. On the other hand, if the de Broglie wavelength for a particular gas of atoms is small compared to this interparticle separation, then that just means we can use classical mechanics. So that's the key lesson from this lecture. And you can make this quantitative by just saying that you can expect classical statistics to apply when the interparticle separation S is much, much greater than the wavelength, the thermal de Broglie wavelength lambda. So you can quantify that in a very straightforward way. From the previous slide, we've got our expression for the de Broglie wavelength. We also have our expression for the interparticle separation distance S. So we can ask what condition has to be satisfied so that the interparticle separation distance S is much, much greater than the Broglie wavelength. And there's a few lines of algebra that follows, and basically the condition is comes down to the number density of particles in the system. When this number density n is much, much less than this quantity that I've written down here, if this condition is met, then you have to use classical statistics. If this condition is false, that requires you to use quantum statistics. And so, right, you have these different regimes, right? When the interparticle separation is much, much smaller than the de Broglie wavelength, you've got wave function overlap. The particles become indistinguishable. You have to use quantum statistics. On the other hand, if the interparticle separation is much, much greater than the wavelength lambda, then the particles are distinguishable, and you can get by with classical concepts. And then there's, of course, a transition region where S is on the order of lambda, and so you go from a quantum regime to a classical regime. It's a continuum, right? There's no hard and fast boundaries here. So it's useful to work through some examples. You can check my numbers at home. The first example is a nitrogen molecule. So this is 2 nitrogen atoms at 300 degrees Kelvin. You can look up the mass of a nitrogen molecule. It's about 4.7 times 10 to the minus 26 kilograms. And we're just asking the question, is the number density of nitrogen molecules at 300 Kelvin and at standard pressure, is that much, much less than this quantity, which is related to the de Broglie wavelength? We've already calculated that at standard temperature and pressure, you've got about 2.7 times 10 to the 25th gas atoms or gas molecules per cubic meter. So this number comes from a few slides prior to this one. What we have to do now is we have to evaluate this rather complicated expression here, and I just worked through the arithmetic, and at the end of the day, I get the condition that 1 has to be much, much less than 4.3 times 10 to the 5th. Well, I think most of you would agree that 1 is small compared to 430,000, which is what this number is. And so since this condition is met, this just simply means that you can treat a collection of nitrogen molecules using classical statistics. The next example I worked through is for liquid helium at a temperature of 2 Kelvin. So this is very low, very cold helium gas atoms. In fact, the gas atoms are so cold that they condense from the gas phase. So they condense from gaseous helium into liquid helium, right? You can look up the density of liquid helium. It's about 0.12 grams per cubic centimeter. The mass of the helium atom can be looked up. It's about 6.6 times 10 to the minus 27 kilograms. And I just want to run through the calculation again to see whether I have to use classical statistics or quantum statistics to describe this case of liquid helium at 2 Kelvin. You can check my numbers, you can run through the calculation, but at the end of the day, I get this condition that 1 must be much, much less than 12, and that's probably not true, because the much, much less typically means a factor of 100 or so. So these two numbers are comparable to one another, and that just simply means that you probably are going to require quantum statistics to describe liquid helium near 2 Kelvin. So that's how you use this criterion to decide whether you've got a classical or a quantum system, right? It's pretty straightforward. It's just an evaluation of a standard equation using the appropriate parameters. The results can be systematized by doing a systematic plot. So this plot, I plot the mass of the particles of interest on a log scale. I also plot the thermal de Broglie wavelength in nanometers, also on a log scale. And I just evaluate that equation on the previous slide for different temperatures. So in this case, I've done 10 Kelvin, 300 Kelvin, 1,000 Kelvin, right? And so you can see what happens is the temperature increases, this linear curve pushes down further this way. And since this axis is telling me the de Broglie wavelength, the thermal de Broglie wavelength, due to these different temperatures. So for instance, if I have a gas at 10 Kelvin, the thermal de Broglie wavelength of a particle with a mass of 10 to the minus 23 kilograms, that the thermal de Broglie wavelength is about 0.05 nanometers, which is what I get by taking this point and extrapolating over. So you have to then include on this diagram the interparticle separation distance S, and the value that you use for S is going to depend on whether you're dealing with a gas, a liquid, or a solid. So for typical gases, S is on the order of 2 nanometers, so that's indicated by this dashed red line. For a typical crystalline solid, S is on the order of a couple tenths of a nanometer, so that's indicated by this dashed line here. And then you can start to put on this curve different atoms, different particles, and see whether for a given temperature that thermal de Broglie wavelength, whether it's greater or less than the typical separation distance S between those particles in let's say a solid or a liquid or a gas. And I mean, let's see. We've already done the case of nitrogen, so let's review that very quickly. So nitrogen has a mass that's indicated by this vertical line here. If you're at a temperature of 300 Kelvin, the thermal de Broglie wavelength of a nitrogen molecule is on the order of 0.05 nanometers. That's much smaller than the typical separation distance S between gas atoms. That's the typical gas atom separation is on the order of 2 nanometers. So because this point here at 300 Kelvin is below S, that's telling you that for nitrogen molecules you can probably use classical statistics, right? The situation is really different when you look at electrons, because the electron mass is very small. It's about 9 times 10 to the minus 31 kilograms. And you can see that for all temperatures that I've plotted, right, the thermal de Broglie wavelength of an electron is greater than the typical separation between atoms in a crystal. So if you pack atoms together to make a solid, typically the interparticle separation is down here. All these thermal de Broglie wavelengths for the temperatures I've considered are greater than this interparticle separation distance. And so that just is telling you that for electrons in solids, you probably have to use quantum mechanics. So this is a very simple way to make this call. It's not as arbitrary as perhaps it's been in the previous lectures. This is an attempt to quantify this very simple idea, okay? So you have to think about this a little bit, but you should be able, after you listen to this lecture, to decide if I give you a system of atoms at a particular temperature, you should, and a particular density. You got to know how many gas atoms there are per cubic meter. You should be able to take that information and then make a prediction about whether the system is going to be governed by classical or quantum statistics. So the last lecture in the statistical physics part of this course is coming up next. And in that lecture, we're actually going to tie together a lot of loose ends. And we're going to tell you what the actual distribution of particles is for a quantum system. We're going to consider two cases. One case is for the particles described by integer spin. That's going to be the case for bosons. The other case we'll consider is for electrons, which particles have spin 1/2. Those particles are referred to as fermions. And we're going to see that the statistics that govern these two quantum particles are completely different. And that'll be the subject of the next lecture. So we'll tie a lot of loose ends up. Please come back and listen to that. It's probably one of the more important lectures in this string of lectures that have been devoted to discussing the statistical treatment of quantum systems. So we'll see you when that lecture begins.